Cloud. Okay. Last section of chapter 11. Woohoo! It's been a long chapter. Way over here. Okay. So last section, 11.8, we are going to talk about combinations. And actually, we broached this a little bit because I was asked last time about, hey, what happens if order does not matter in some situation? And that is what the idea of a combination is. So on the sheet that you have, or if you're watching the video, the sheet that you hopefully printed, we're just going to go through a combination. Combination is an arrangement of objects in which order is not important. Okay, so just going to write this down so I feel like I'm being a good instructor today. My pen is squeaky and bothering me. I got a lot of stuff going on here today. So the key, if you remember from what we talked about last time, permutations. Permutations was an arrangement of objects in which order is important. So meaning if an element came first, that was significant. If it came second, there was significant. And so one of the examples was we were picking people and they were going to be a president or a vice president or a treasurer or something like that. So if you got picked first, it meant something. There's a hierarchy. There's an order that matters in the picking. For a combination, the order is not important. Now you might say, hey, Herster, when I was in high school on my locker, I had a combination lock, but I had to put in the numbers in an order. And the answer is yes. Combination locks mathematically should really be called permutation locks, okay? Because the order matters. Did you have a question?
Yeah, I was gonna ask, like, whenever you get there's the difference that like everybody gets the same thing.
Mm-hmm. Yeah, that's one of the differences. Everyone will get the same thing. So for instance, here's an example. If there was a raffle, and we had a raffle in which the first place was $100, the second place was $50, the third place was $25. That would be a permutation. Order would be important, right? Because you'd want to be picked first or second or third. There would be a difference. Or we had a raffle where there was three $50 prizes. Would order matter then? If you were picked first, second, or third, if there was three $50 prizes? No, because you're going to get the same thing no matter what. So that would be kind of a situation where the second one will be a permutation because order would not matter at all. Does that make sense? Okay, so that's what we're looking for as we go through these problem stuff. And one of the things I mentioned to you about doing the homework for the permutation. So if you haven't done that homework yet, when you're going through 11.7, make sure when you're doing the problem, you say, now why is order important on this problem? What about this problem is communicating to me that it's a permutation? So that way, when you get to the combination section, okay, you can see the difference. Okay, because on the test, I'm just gonna have a few problems. I'm not gonna tell you one way or the other, but I will make it clear. It's not gonna be a guessing game on whether it's one or the other. Okay, so here let's demonstrate the difference. So on the sheet, I said let's consider this set right here: A, B, C, and D. And so what we're going to do, and what you're going to do, I'm going to give you 2 minutes to do the best job of this you can. What we're going to do is we're going to pick 2 letters out of the 4. So first, let's list all the permutations. So all the permutations, meaning it matters what order the letters are in. And we know from the counting principle, if we're going to pick 2 letters, okay, how many choices do I have for the first letter? 4. And then how many choices do I have for the second letter? 3. So 4 times 3, you should have 12 things listed here for your permutation. So do your best to list all 12. Okay, 2 minutes. All 12 combinations of like all 12 permutations. Yes. Oh, yes. Yes, order is important. Well, in this situation, what order being important would mean, I'll help get you started. what order being important would mean is that A and B is a different situation than B and A, that those would be distinct choices. Okay, that's what it means for order to be important. Okay, so got you started. A and B. So there's A and B, and then we can flip it around D and A. Those are order being important means those are two completely different outcomes. Okay. And then we have A and C, and then I can flip that around, C and A. Then I have A and D, and then flip that around, D and A. So there's 6 of the 12, because we know there's going to be 12, 4 times 3, 4 choices for the first one, 3 choices for the second one, so 12. So I've done all the ones with A, so now I've got B and C, and I'll flip that around, C and B. Then I have B and D, and then I'll flip that around, D and B. And then finally, I have C, and then flip it around, DC. So there's my 12 options. Another way you could have done that, I just did it from my head, but maybe you were like, hey, I remember a section where we actually talked about this. You could have done a tree diagram and said your first choice, okay, so for your first choice would be A, B, C, and D, and then your second choice, if you pick A, would be B, C, or D, and then that would give you all 12. That would give you all 12. So tree diagram. That'll be something we review if there's some time at the end. Okay, so then the next thing is, okay, that's what the permutations look like. Those are the 12 options if I consider order, if that is important to me. But now combinations, this new thing we're talking about today, combinations is the arrangement where order doesn't matter. And so there's fewer arrangements. And so the arrangements look like this. For a combination, A and B and A mean the exact same thing. There would be no difference in what order you picked those two things. And so for my combinations, I'll just write down that I have, that pen was a fail. I was so excited, I found a brown marker trying to span my horizons. Okay, so AB means the same thing as BA, so I'm just going to write it down once. And then AC means the same thing as CA, so I'm going to write it down once. AD means the same thing as DA. BC means the same thing as CB. BD, same thing as DB, and then CD. So what we see is where there were 12 permutations. Now we've reduced it, since order doesn't matter, there's only 6 combinations. Okay, so it changes for us. So I know you were just about to ask a question. Is that a little clearer?
Yes, because so combinations are, as long as they have the 2 same like letters or composition, they're the same.
They're the same. Yes. Yes.
Similar.
The order does not
I
matter.
understand what order matters. Like I thought you meant like the order of like the A and B and the A and C, like the order of that. But you talking about the order of the actual like letters?
Right.
Okay.
That's exactly what I mean. So again, just one more time. For a permutation, order mattering means if I get A first and B second, that is a distinct outcome and different than B first and A second. Okay, like words. Words, the order of the letters in words have meaning. Okay, so like what are 2 words that share the same letters? I don't know. I can't think. What's that? Okay, there. Well, no, that's not exactly what I'm meaning, but it would be more like if I have. There you caused me to think. So your example is probably right, but I didn't hear it exactly. But I've got one now. Own and now, right? Permutations. Order matters, right? There's completely different meanings there. Okay, so words are permutations of letters. Combinations means it doesn't matter what the order is as long as I have A and B together. Okay, whether A was first or B was first, doesn't matter. Okay, that is the difference between a permutation and combination. So we're going to look at some examples, but if you remember the permutation formula, when order matters, okay, there is a combination formula when order doesn't matter. Now, the good news, I'm hoping this is good news. The combination formula is just a little change, an addendum to the permutation formula. So here is the way that when you know it's a combination, that you can calculate, like, how would we get 6? I have 4 items, I'm choosing 2. How would we get 6? Well, here's how you would do it. So it's the combination of n items, and I'm choosing r of them. So over there, it's the combination of 4 items, I'm choosing 2. So we're putting numbers to this example that's right over here, that's in purple. I don't know if you can tell in the video, that's purple right there, because I'm trying to be more colorful. Okay, so here we go. So first thing we saw last time is the number of permutations, the number of ordered arrangements if I'm using all the objects. Does anyone remember what the number of ordered arrangements are if you're using all the objects? All n objects. It was, so if I use all n objects, if I have 7 pictures and I hang all 7 pictures on the wall in a line, you remember what we did for that? So there you go, the factorial. So the ordered arrangements of all the objects is n factorial. I'm just gonna make a little note because this is how we've progressed through this. The first thing we looked at was the ordered arrangements when we use all the objects. So what I'm hoping, because I know you got a couple formulas to remember on this test, what I'm hoping is to make it easier to remember and differentiate between these 3 things. So if you have the ordered arrangements, you're using all the objects, it's n factorial. But then we said, okay, the next situation was, what if I don't use all the objects? What if I'm just picking a couple of them? And so then we said, okay, the next thing you did is what did we divide by here to take into account that I wasn't using all the objects? Right, this is n minus r factorial. This is the arrangements. Yep. This is the arrangements of the objects not being used. And then, yes, you're exactly right. The way it stands now, that's the permutation formula. So again, these formulas just kind of build on each other. This is permutations when you're using all the objects. Then we put this on when we're not using all the objects. This is the objects I'm discarding. And then here's the final thing. This is what makes it the combination formula. What I now have to do is I have to account for all the duplicates. I have to divide out the duplicates. And the way you divide out the duplicates here is you do r factorial. Remember, r is the number of objects I'm using. And so what I'm doing is I'm dividing the duplicate arrangements of the objects I'm using.
So are you going to multiply whatever you get in the parentheses by or r factorial?
This is going to be a number factorial. There'll be a number, and then you multiply by that. Or if you have a calculator that does this, there is a NCR button on your calculator. If you have a PRB button, if you have a graph, I see a couple of you have graphing calculators, you definitely have it. Most of the TI calculators, the different formats have a PRB button on it, and so it'll be in the menu. I don't really know about all the Casio calculators, but yes. So we're going to put some numbers to this and make this a little easier to manage. So here's my example. Example 1. Example 1 says this. In a class you are taking, you are assigned to read any 3 books from a list of 8. It doesn't say It doesn't say you get 50 points for the first book and 25 points for the second and 10. That there would be a hierarchy there, right? All this says is you're picking any 3 books from a list of 8. How many ways you can do that? Okay, so again, as we're reading these problems, I just want you to make sure you're comfortable understanding why order is not important. There's no hierarchy. There's no first, second, third. There's no best or second best or favorite or something like that. There's no order. So this is a combination problem. So this is the combination of 8 objects. There's 8 books, and I'm choosing 3. Order is not important. Okay, so whether I read, I don't even know. We talked about, wasn't this the class we talked about different books that we were reading? So whether you talk about Lord of the Flies and The Great Gatsby and The Sun Also Rises, those were the ones I had to read in high school. So, or whether you do them in a different order does not matter. Okay, any 3 books. That's why this is a combination problem. Yeah.
But if it was like a book series, it would matter, right?
Right. If I gave some indication that there was going to be a hierarchy, right? If you had to pick a week, you were going to read 3 books. So it mattered when you were going to pick them because that was going to be the order you read them. Or if I was going to assign some sort of value, like you get the most credit for the first one you read and less credit for the second, if there was some way that that order was going to be important. All right, so here we go. So then if I was reading all 8 books, that would be 8 factorial. That's first. And then I've got to get rid of the arrangements of the 5 books I'm not reading. So that would be 8 minus 3 factorial. That's the permutation formula. If order mattered, we'd be done. But order doesn't matter in this situation. So what I have to do is I have to divide out the duplicate arrangements of the 3 that I'm choosing. So I divide out the 3 factorial right there. So if you have a calculator that does this, you're done with the problem. Okay, this is what I want to see on the test when you take the test on Tuesday, and then you can go to your calculator and you can come up with the number right there. That's fine. Some calculators only do the exclamation point. If you borrow one of my scientific calculators from Dollar Tree, it only does the exclamation point. It doesn't have the C button or the P button for permutations. So then what you would do is you would put 8 factorial in the calculator and then 5 factorial, 3 factorial, and then just do the division of those numbers. And then if you don't have a calculator that does any of those things, then what you're doing is this. 8 factorial is 8 times 7 times 6 times 5. I'm stopping at 5 factorial because that's what this is. And they're going to cancel. And then 3 factorial is 3 times 2 times 1. So 5 factorial cancels with the 5 factorial there. 3 times 2 is 6, and that cancels with the 6. So 8 times 7 is all that's left over, and 8 times 7 is 56. There are 56 different groups of 3 books that you can pick out of those 8. 3 times 2 is 6, and I just canceled it with the 6 up there. And then when I was listing out 8 factorial, I stopped at the 5. Instead of writing the 5 times 4 times 3 times 2 times 1, I realized that 5 times 4 times 3 times 2 times 1 there is just what this is, 5 times 4 times 3 times 2 times 1. It's tough to say all that really fast. All right. So if your calculator doesn't do any exclamation points, that's what you have to do. Better? Yes. Better? We doing okay? Let me know, please. That's why we're here. We've got 6 examples to do, then we're going to do some reviewing. Okay, so do example 2. You're going to the ice cream shop, which sounds really good right now. Maybe the food truck that comes today will be the ice cream truck. Park right over here behind the student center in the parking lot. Yeah, so that when I'm teaching class, I can see them and I can see all the people and all the food, and I'm in here. I have 4 in-person classes, so I just teach 2 each day, and then I have 3 online classes. Okay, so this problem says you're in an ice cream parlor and it has 20 flavors, or you're not there, Cynthia's there. Cynthia orders a banana split, and for whatever reason, the policy of the store, she has to select three different flavors. Okay, so we're just trying to make sure that the problem's not impossible for us to do with our skills. And so how many different selections can we make here? Okay, so it's a combination problem because it doesn't say that she's picking a favorite or a second favorite. It just says we're putting 3 flavors in a bowl. Okay, so it doesn't matter what order that these things happen. So there are 20 flavors to choose from, and we are choosing 3. Yeah.
So I guess it's something like a cone where like one will be at the bottom and the middle is probably spin on that.
I mean, that's a great question. If I made a question like that on the test, thinking order didn't matter, and you argued passionately that order does matter because whatever's closest to the cone is going to have the best flavor, right? So I would give you credit for that. Okay, but yeah, I can see. I would probably say, yeah, a cone would be order because there's a hierarchy. So we're just throwing things in a bowl here. So order is not important in this particular problem. Okay, great. So I try to be super careful when I'm designing the problems and make it really obvious that order matters or doesn't. You know, like I'm fond in the permutations, I'm fond of the problems that say there's a first or second or third or president or vice president, just so that you know without a doubt that there's an order to what you're choosing. And so, all right, so here we go. My total number of objects is 20, so 20 factorial. The objects I'm not choosing are 20 minus 3, or 17 factorial. So these are the objects not chosen. And then I have to divide out the repetition of the 3 that I am choosing. So there we go. So once again, if you have a calculator that does it, you are done with the hard work of the problem. If you don't know how to enter this into your calculator, I helped a couple of you last time. That is totally fine. And if you do have just the Apple calculator, I was just looking on my phone, not that you can use this on the test, but if you're using it on homework, the Apple calculator only has an exclamation point. So then you would do each of these 3 numbers individually and then just do the arithmetic. But here we go. I've got 20 factorial times 19 times 18, and then 17 down to 1 is 17 factorial. And the reason I stopped there is because that's what this is. So that makes life a little more convenient. And then 3 factorial is 3 times 2 times 1. So here the 17s go away. Again, 3 times 2 is 6, and 6 goes into 18 and leaves 3. And so I'm just trying to, this is not a required step. I'm just trying to show you that it's not the worst thing in the world if your calculator doesn't do it. The arithmetic usually works out to be pretty straightforward, especially with the numbers that we are using. So that is 20 times 19 times 3, and that is 1,140 different ways. All right, here's the do example 3. Same sort of thing. We're just practicing with this formula. Yeah.
So here, when you do the 20 minus 3, like what are the specific things again? The repetition and the total amount minus repetition.
This right here is the arrangements of the objects I'm not using.
Okay.
So this is in this particular problem, this is the arrangements of the 17 flavors I'm not choosing. Then since order doesn't matter because I'm just putting them in a bowl, this is dividing out the repeated, like vanilla chocolate strawberry is no different than chocolate vanilla strawberry or strawberry chocolate vanilla. Those are all the same thing. So I'm dividing out all the repetition. That's what this is.
And then, so you're going to get like the 17 factor. You're going to get 2 of those, or you can cancel out every time, right? Okay.
Yep. That's good. That's the way it's worked. These past 2 problems is the way they'll always work on these formulas. Okay, so the arithmetic, you should always end up with a whole number. You're not going to have a decimal or a fraction. If you do that, then you've done something wrong in your canceling or calculator. So go ahead and do example 3.
4 out of 7, is that like part of the?
Oh, you know what? That's a typo.
Okay.
That should say 4 out of 9. Sorry, everybody. So if you're watching on the video, the end of the problem where it says 4 out of 7, it should say 4 out of 9. I'll try to correct it before I post it on Canvas. It was early to be typing. That was the problem. All right, so Paul has 9 CDs, and we don't even really use those anymore, but that's okay. We need to have a problem. And wants to choose 4 of them to take the work. How many ways can Paul select 4 out of the 9 CDs? So we had to make that correction. So again, we are not told that he's choosing favorites. We're not told that he's, if you remember the old school CD players, we're not told he's putting 1 disc in the first slot and 1 in the second. There's no implied hierarchy. You remember those? Yeah, okay, great. I'm glad I'm not the only one. Okay, so this is a combination problem. There's no indication that order matters here. He's not choosing a favorite and a second favorite. So there are 9 CDs, and we are randomly choosing 4 of them, and we want to know how many groups of 4 can Paul take to work with him. So here goes. So the arrangements of all 9 objects are 9 factorial. Then I've got to take away the 9 minus 4, the 5 objects I'm not using, the 5 CDs are not being used. And then I got to get rid of the duplicates of the 4 that are being chosen. So again, if you got the calculator that does it, you're done with the problem. But 9 factorial is 9 times 8 times 7 times 6. And 5, 4, 3, 2, 1 is just 5 factorial. 9 minus 4 here is 5 factorial. And then 4 is 4 times 3 times 2 times 1. So rid of that. And then it doesn't matter what order you do this in, there'll always be enough to cancel out. So I'm just going to go 3 times 2 again is 6, so cancels with that. And then 4 will go into 8 twice. So then I'm left with 7 times 2 is 14. 14 times 9 is 126. That's what I was going to say. But I didn't. All right, so to flip the page, we're still doing combinations, but then there's one more type of problem. It's combining something we talked about last time. So now what we're going to do is we're going to involve the counting principle. So if you look on your last sheet from section 11.7, then you remember the counting principle says this. We've talked about the counting principle twice in this unit. This is the 3rd time. Counting principle says if there are m ways that a first thing can happen, and then there's n ways a second thing can happen, then when I combine them, the total number of ways is m times n. Okay, so the first example we did was I flipped a coin. There was 2 ways for that to happen. I rolled a die. There were 6 ways for that to happen. So the total number of ways, if I do the things together, 2 times 6 is 12. I mention that because example 4, I'm going to do example 4 with you. You go to a restaurant and you're going to order a family style dinner. And the way you do that is you're going to select 3 out of 5 appetizers. You're going to select 4 out of 7 main dishes and 2 out of 6 desserts. And so what we want to know is how many different ways are there for you to order dinner. Okay, so again, we're not told that there's any sort of hierarchy here. They're not saying the first one you order costs more than the next. So the way the counting principle is involved here is this. What we're going to do to figure out the total ways to order dinner is we're going to first figure out how many ways to order the appetizers. We'll abbreviate that. And then we need to figure out how many ways to order dinner. Or what did I call it on here? I called it main dishes. And then what you're going to do is how many ways to order dessert. 2 S's in dessert. We don't want to order a desert. And then we're going to use the counting principle. If however many ways there are to do this, and however many ways to do this, and however many ways to do that, the number of ways to do them all together is to multiply these 3 things together. So it's involving 2 things. It's involving what we just talked about with combinations, and then the counting principle from previous. So here we go. How many ways can I select 3 out of the 5 appetizers? So since there's no order, it's a combination problem, and I have 5 appetizers, and I've been asked to choose 3. Times main dishes. How many ways can I choose 4 out of the 7? So I have 7 main dishes. I have to choose 4. And then last but not least, how many ways to choose desserts? There are 6 desserts, and I am choosing 2 of them. So I have to do the combination formula 3 times on this problem. This is where if you have a calculator that actually does it, it's going to save you a couple of seconds. But if you don't, it's doable. All right, so here we go. For the first one, for the appetizers, I've got 5 factorial. 5 minus 3 is the appetizers I'm not choosing. And then 3 factorial, those are the duplicates of the 3 that I am. For the main dishes, I've got 7 of them, so 7 factorial. 7 minus 4 are the ones that I'm not choosing. And then 4 factorial are the duplicates of the ones that I am. And then last but not least, desserts, I've got 6 of them, so 6 factorial. 6 minus 4 are the ones I'm not choosing, and then 2 factorial are the duplicates of the ones that I am. Now, is everyone comfortable with the formula? Are we having any problems coming up with the number? Because I'm just going to ask one of you that has the calculator that does this, say, give me the numbers. Are we okay with this? Okay. So, what is 5? Choose 3 here. What? 10? So there's 10 ways to choose appetizers. Okay, great.
35.
35, there's 35 ways to choose main dishes.
15.
And then 15. So 10 times 5 is 350, times 15 is something.
5, 2, 5, 2.
5, 2,
So you multiply them all together.
Yep, because it's the counting principle. We figured out individually how many ways there were to do each of the 3 things. Then the counting principle says, if there are n ways to do a first thing, and there are n ways to do a second thing, then the number of ways to do them together is to multiply. And so then we have a third thing here, so you multiply again. Okay, it's the same thing as when we flipped a coin and rolled a die. 2 ways to flip a coin, 6 ways to roll a die, so 12 ways to do them all together. And so that's what's going on here, just in a little bit more complicated of a situation. So just to make sure we're working things out, because I don't want to just leave it at this, you're going to do example 5. You're taking a test. We all hate these tests. I always hated these tests. You got to pick 3 out of 5 questions in part 1. You've got to pick 4 out of 8 questions in part 2. You can do it in any order, so it's explicit that the order doesn't matter. How many different ways are there to complete this test? All right, so for this test, you've got how many ways can you do part one? And then times how many ways can you do part two? So to do part one, okay, so here's a common mistake. I'm just thinking of this because it's been like a year and a half since I've taught this class live. Common mistake, and this is wrong, is you can't just say, oh, okay, if there's 5 questions in part one and 8 in part two, then that's 13 altogether. And then if I'm picking 3 in part one and I'm picking 4 in part two, then I'm picking 7. You can't do this just in one hop like that, because you're not picking equally. You got to pick a certain number in the first part and a certain number in the second part. And if you did it all as one, you wouldn't be accounting for that. So it has to be done in 2 separate steps like this. So in part one, okay, we are told in any order. So I have 5 questions. I have to choose 3. In part two, I have 8 questions and I'm choosing 4. So for part one, there are 5 questions. That's 5 factorial. I am not choosing 2 of the questions, so that's 5 minus 3. And then the duplicate arrangements, because order doesn't matter, is 3 factorial. And then times 8 questions in the second part, 8 minus 4, those are the 4 questions I'm not choosing. And then 4 factorial, that's the duplicate arrangements of the 4 that I am choosing. And then I'm going to ask you to throw it in your calculator. What did you get for, well, I guess we just did this over there. That's 10. And then what's 8 combinations when you're choosing 4? 70. So there are 700 different ways that you can take that test. There are 700 different groups that you can make. All right, last one. Last question for this section. So if you got anything on your mind about it, let me know. Do example 6. You are helping an adoption agency plan their newsletter. All right, so for this problem, it's the number of ways I can choose cats times the number of ways I can choose dogs. So for cats, there are 15 of them. I'm choosing 6. So 15 factorial, that's my total number of cats. 15 minus 6 are the total, those are the 9 cats not being used in the newsletter. And then 6, that's the duplicate arrangements of the 6 that I am. Over here, dogs, same thing, 12 factorial. 12 minus 4 are the 8 dogs not being featured. And then 4 factorial is, that's the duplicate arrangements because order does not matter here. And so when you pop into your calculator, 15 combination 6, how many is that?
5,005.
That's a lot. And then this one's 455, you said?
495.
495? And then when you multiply 5,005 times 495, you're gonna get a large number, and what is that?
2,477,475.
That was said with such confidence. We good? We have confirmation of that? Excellent, I feel great about it. All right, that's combinations.